Okay, so let's say that we have a charged capacitor that we then connect to an inductor, inductance L, but also to a resistor of resistance R, like that. How does the charge behave in time? So, right, the principle is the same as we've seen before, right? Despite the time dependence, when we integrate around the entire circuit, because the charge that matters is because the electric field that comes into this calculation is the electric field produced by actual charged particles that diverge radially away or towards those particles, then this principle must apply. And it takes the form of the voltage across the inductor, the voltage across the capacitor, where capital Q now represents the charge at some moment in time, plus the voltage across the resistor, that has to add up to 0. But again, this and this, the current and the charge, are not independent, and so if we want to write current in terms of charge, we really have a second derivative here. So we end up with two derivatives of charge. Let's pull this L, let's divide everything by L, so we start to isolate the second derivative term, plus, let's actually sort of order this so that we have two derivatives in charge, one derivative in charge and charge itself. So we'll put this term here. So we have R, but we've divided by L, everything by L. So we have R over L. The I is dQ by dt. And now we can have this term. We've divided by L, so we get 1 over LC, and we have charge itself. Well, now that I've used little q, let me write little q here. That's actually what I've been doing all along. So Q over there, so we have Q like that, and that's equal to 0. So the question is, what's the solution to that equation? And what we want to do is to think of what the solutions have been to combinations of R, L, and C. And the argument will be that these solutions are all exponential solutions. And so the general solution must also be an exponential solution, and that'll make life easier for us when we try to solve for this system. So notice that when we had when we had no resistor, we had an LC circuit, then the charge in the capacitor behaved according to an equation that looks like this: cosine of T over LC square root plus phi. This doesn't look like an exponential, but it actually can be written as capital Q exponential with some, let's make this a slightly different I, e to the I omega, omega is, I wrote it as 1 over the square root of LC, so let's keep that. T over the square root of LC plus phi, where now we don't need to worry about these complex numbers, but this is actually the square root of -1. Very strange kind of object. But it can be shown that a cosine function can be written in this way. When we have an RL circuit, right, and there's no capacitor, we've shown that the current looks like I naught e to the minus RT over L. That's clearly an exponential. we've shown that when we have the RC circuit, the charge goes like Q naught e to the minus t over RC. And so this, and this, these are all exponential solutions. And so in general, the solution can be written in terms of e to some a times t. Now the question is, what is that a? So a could be, so with a being real and negative, so we saw that it was negative, right, in some of these cases. A can be real and negative, or it can be have this weird object here, and that's an imaginary number. It can be imaginary. Okay, when it's imaginary, then you get the sinusoidal behavior, right? Otherwise, you get the exponential decay behavior. So what we want to do next is to place this kind of solution. This is the general solution. It'll have some coefficient, call it b, that's really some charge, e to the a times t into our equation, into this equation, and see what constraints we get on a. dq by dt is equal to, we take a derivative, ab e to the at, and two derivatives of this gives us the a squared, b e to the at. So now we'll put this into the equation. So let's plug, right, we're going to put this into here. We're going to put this into here, and we're going to put this into here, and see that we get a constraint on this exponential term. So what does that look like? So we get an a squared be to the at. We always get the be to the at term back. We can cancel all those out, but let's just write them out. Then we have an r over l ab e to the at plus a 1 over lc b e to the at, and that must equal to 0. And so once we cancel out the common be to the at, we just get an a squared plus an r over la plus 1 over lc, that's equal to 0. And we can see that this is a quadratic equation for this a quantity. And the solution is therefore a equals minus r over l plus or minus the square root of r over l squared minus 4 times 1 over lc, all divided by 2. Or we can write this as a equals minus r over 2l, right? So there's a negative exponential term. This is an exponential decay, plus or minus 1/2 of the square root quantity. And this here is where you determine whether you have only exponential decay or you have oscillations. Right, so oscillations can exist only if this becomes an imaginary number, right? Because imaginary numbers are associated with cosine functions or sine functions. Cosine or oscillations, right? So it's possible the cosine represents an oscillation. So oscillations exist if we get a negative number under the square root. And that means that r squared over l squared, which is this, minus 4 over lc, is less than 0. And the condition on that is, well, we'll bring this to the other side. We'll take the square root. How do we want to write that? We can write it as r squared has to be less than 4 over l, 4l over c. and we can take the square root of that. So r is less than 2L over C square root. If this is true, if the resistance is small enough, you'll get oscillations. But this term never goes away. So it's not possible to get rid of the exponential decay. Once you have a resistor, R is not equal to 0, you can't get rid of exponential decay. And so in other words, the solution involves Q to the, e to the minus R over 2L T, and an e to the, of course there's a plus or minus there, so plus or minus 1/2 times this square root term times t. This could be an imaginary number, right? It could be I, and so that could involve a cosine. So you could get a solution that looks like this. You can't get rid of the exponential decay, so the Q is proportional to this times, there could be a cosine function there, right? If this is imaginary. And so you have at the same time oscillations, but exponential decay. And we'll explore that.